here's the Tollens reduction reaction. You can see the ammonia complex of silver, and then this is glucose aldehyde that's reducing it to a metallic silver mirror. So here, this is the complex of silver and ammonia, and we're adding the glucose solution to it, and it turns this amber color. And then after it sits there for a couple minutes, it turns into this silver mirror. And here, I'll pass this around so you can see it. But it turns this silver mirror that kind of coats the inside of the flask. Here's the reduction of copper 2 chloride by glycerol. The copper 2 chloride in glycerol is kind of like a green liquid, and we let it heat up to about 170 degrees and then cool off and sit there, and the copper 1 chloride precipitated out of it into this layer at the bottom with this dark liquid on top. And then we washed the copper 1 chloride with ethanol and dried it, and so it created this powdery substance with the copper 1 chloride. So vitamin C is an antioxidant, meaning that it is a reducing agent, meaning that whenever it is reducing something else, the vitamin C is being oxidized. So through it gives up like protons and electrons. So we analyzed vitamin C at 2 different pHs with a cyclic voltammetry, and so here are our results. We found that with a lower pH, it had a higher oxidation potential. So with a pH of 7, it had an oxidation potential of 0.6 volts, and then with a pH of 1.4, it had an oxidation potential of about 0.73 volts. And this is important because when you are trying to reduce the metals out of these species of metal ions that have positive reducing potentials, you need something with a negative reducing potential. And so you can have a greater reducing potential if you have a lower pH vitamin C. So here we're adding the vitamin C to silver, and you can see that that black cloud forms. It's black because it's a pulverized metal, and that's at a pH of 7. And then we're adding vitamin C again to the ammonia complex of silver, and it reacts much quicker, it turns darker. Now it's pH of 12. So there is an industry in which companies will take used catalytic converters and pull the noble metals out of them, like gold, platinum, palladium, rhodium. And they do this through a process called the cupellation process. And it's been used for a really long time. It's the most reliable and accurate to determine the content of platinum, palladium, and rhodium. And so basically what they do is they take the material containing the noble metals, they treat it with lead oxide and corn flour, and then they heat it to really high temperatures. And the noble metals in it will dissolve in lead, and then this lead chunk is separated from all the extra stuff that they call slag. And like a small amount of gold is added to the lead chunk, and then the lead is put into this magnesium oxide crucible. And the magnesium oxide crucible will suck all the lead oxide out, leaving just the noble metals in a little pellet. So here's the process, and this is the extra slag that they separate out. That's the little lead. You can put it in the white thing is the magnesium oxide crucible, and it turns yellow because lead oxide's yellow. It sucks out all the lead oxide, just leaving the noble metals in that little pellet. So this little pellet is taken and dissolved in a liquid called aqua regia, which is a 3-to-1 ratio of nitric acid and hydrochloric acid. And that is taken, and a little bit of the sample is taken to use in an ICP analysis. And it doesn't take a lot of the solution in order to analyze it in the ICP. So most of the solution remains, and you can get a lot of the noble metals back out of it. So, but in order to recover it out of this liquid, like, because metals are hard, they're not liquid. So how are you going to get the solid metal back out of it? You have to precipitate it out of the liquid with a reducing agent, which is the point of this talk. So you take the stock solution, and our stock solution had a concentration of about 3 grams of gold in 1 liter, and that's about what it normally is. The amount of gold is much higher than the platinum, palladium, and rhodium that's in it. And so in 1 liter of this solution, it's got about $140 worth of gold. And there is a company in Anniston called Multi-Metco, and they do this every day, every week, and they produce about a gallon a week, so like over $500 in gold from their solutions. So here we're adding vitamin C to this stock solution. It's got that yellow color because of the amount of gold in it. And you can see that it takes way more vitamin C than the rest of the solutions that we've added to start reacting, but it turns this dark color, and that's reacting. And then we precipitate out, so you put it in the centrifuge, dry it, and this precipitate you put under an electron microscope, and this is the picture at the top on the right. And it's black because any kind of metal that's ground up into a fine powder is black. And then this chemical analysis right here, you can see this peak right here and these peaks right here is the amount of gold in the sample. And you can see how much higher it is than the rest of the platinum, palladium, and rhodium in the sample. So the results. Why do we care about all of this? So the stock solution had had these numbers of ppms of the gold, platinum, palladium, and rhodium in it. And the 2 methods, vitamin C, zinc, and aluminum, had different results for how much it pulled out of the solution. The vitamin C pulled out pretty much all the gold, and then pretty much all the palladium, and then it pulled out platinum when it was heated up. The vitamin C was heated up. It didn't really pull out that much rhodium. And then the zinc and aluminum with sugar and glucose pulled out pretty much relatively all of it. So why do we care about any of this? The zinc and aluminum will precipitate all gold, platinum, palladium, and rhodium, but this precipitate is then contaminated with an excess of zinc and aluminum because you have to put so much in it in order to get a precipitate. It also produces hazardous waste like zinc chloride and zinc nitrate. It also produces flammable hydrogen. And this reaction takes a really long time, several hours to do. So then vitamin C does not produce hazardous waste. It does not produce flammable hydrogen. It does precipitate only the gold and the palladium, but it partially precipitates platinum and rhodium, and that's probably due to soluble complexes that it forms with platinum and rhodium. But platinum can be precipitated just only with the hot solutions. And then this reaction goes really quickly. It only takes a couple minutes to do. So why we care about this? I keep asking that. You're going, what? I don't care about any of this. But this is all for these kinds of industries that do this sort of thing on a daily basis. They have to compare the cost efficiency. They have to compare, is it worth it to contaminate the environment with all of this hazardous waste that we're producing? So they have to look at this kind of thing to determine which route they'd rather take. So I'd like to thank the JSU Department of Chemistry and Geosciences for allowing me to conduct this research. Oh, yes, I'm sorry. This is also, I'll pass this around too, but this is the precipitate that we actually got. This is a gold, platinum, palladium, rhodium. I almost forgot. I'd also like to thank Multi-Metco for letting me do some of my research there because they have an ICP machine, and Chris Loveless for helping me to run all the experiments. So, any questions?
How much is this worth?
I
$10.
That's a
It's
lot of
pretty
work,
heavy.
$10.
You know, it's pretty heavy. It's about 100 milligrams. So it's about $10. Actually more for the tea.
You can auction it off. Oh, just a question.
Yes.
Sorry. So with all of your research, do you think that it would be comparable to like replace vitamin C in the industry instead of using the other?
Possibly. It would take a lot for like a company like Multimeco to kind of switch over their entire process of doing it. But I mean, I think it's worth looking into so that they can, you know, because the amount of rhodium that they have in the sample is only 10 milligrams per liter, and I mean, they wouldn't be really getting that much money back for that much amount of money if they're just, or for that amount in the sample. How much environmental waste they're using.
So I'm assuming that they currently do it that
Other way.
the other
They
way.
add zinc and aluminum to it, and
Okay.
it kind of spins and sits, and then it creates this like sludge,
Right.
and then they separate out the,
Which also then produces those
Yeah.
toxic chemicals that you were speaking of.
yes.
If I may add something, because this is something legal actually. The problem is that in order to do anything here, you need to get a number of permits. For example, they had to get a permit for using zinc and so on and so on. Now, in order to do vitamin C, you need to start this process all over, which will take a lot of time and so on, because you need to prove that you are basically, you know, a lot of things, okay?
Right.
And this requires expertise and so on and so on and so on and so on. So this is why industry is not very eager
To change.
to change. That's a problem. It's a big problem.
I can see how.
I'm also very happy to see, it's unusual for a JSU alum to come back and work, and that connection with the symposium, so
I
that's
work at
really.
Multimeco now, so
Oh.
I